January 9th, 1992. Aleksander Wolszczan is sitting in front of a printout at the Arecibo Observatory in Puerto Rico, and the numbers are wrong. Not wrong in the way that suggests equipment failure, not wrong in the way that suggests a calculation error somewhere upstream. Wrong in a specific, structured, repeating way, the kind of wrong that means something is actually there. He had been tracking a pulsar, a dead star, the remnant of a supernova, spinning so fast it sends out radio pulses with the regularity of an atomic clock. This one, a pulsar cataloged in the standard astronomical registry, was rotating about 9.5 times per second. Wolszczan had been monitoring its timing, the precise interval between each pulse, each rotation, measured to within a fraction of a millisecond, and the intervals were drifting. Not randomly, not chaotically. They were drifting in a pattern. The pulsar appeared to be speeding up slightly, then slowing down slightly, then speeding up again. A rhythm on top of the rhythm, a signal inside the signal. Wolszczan stared at that pattern the way you stare at something when you know you're either about to be very embarrassed or very famous. To understand why that drift was impossible, and then why it was inevitable, you need to understand what a pulsar actually is. When a star between 8 and 20 times the mass of our Sun exhausts its nuclear fuel, it collapses. Not slowly. In less than a second, the core implodes under its own gravity. The outer layers rebound outward in a supernova explosion, one of the most energetic events the universe produces. What's left at the center is a sphere of neutrons, roughly 20 kilometers across, containing more mass than the Sun. 20 kilometers? Hold that. The distance you might drive to a grocery store in a mid-sized city. That is the diameter of an object more massive than the Sun. And it spins. Because the original star was spinning, and conservation of angular momentum is not a suggestion. As the collapsing star's radius shrinks by a factor of tens of thousands, its rotation accelerates proportionally. The same physics that makes a figure skater spin faster when she pulls in her arms, but applied to something collapsing from hundreds of thousands of kilometers down to 20. The result is rotation rates that are physically difficult to hold in the mind. Some pulsars rotate hundreds of times per second. The one Wolszczan was watching rotated about 9.5 times per second, relatively slow as pulsars go, which mattered for what came next. As the pulsar rotates, it emits beams of radio waves from its magnetic poles. If the geometry is right, if Earth happens to lie in the path of one of those beams, we detect a pulse with each rotation, regular as breathing, regular as anything in the universe gets. That regularity is the point. A pulsar is a natural clock, more precise than almost anything humans have built. The interval between pulses is stable enough that astronomers use pulsars to test general relativity, to search for gravitational waves, to calibrate other measurements. When a pulsar's timing drifts, it means something is wrong with the clock, or something outside the clock is pushing on it. In 1992, the only known things that pushed on pulsars were other massive objects, binary companions, other stars locked in orbit, each pulling on the other gravitationally, each causing the other to accelerate and decelerate slightly as they moved through their orbits. That effect has a name. It's called the Rømer delay, after the 17th century Danish astronomer Ole Rømer, who noticed that the moons of Jupiter appeared to arrive slightly earlier or later than expected, depending on whether Earth was moving toward or away from Jupiter. The light, and later the radio pulses, had more or less distance to travel depending on position in the orbit. The timing variations encoded the orbital motion. Wolszczan was looking at timing variations, structured, repeating, mathematically tractable. He ran the numbers for a binary companion, another star in orbit around the pulsar, and the model didn't fit. The variations were too complex. Two separate periodic signals were present, each with its own period, its own amplitude. To account for both simultaneously, you needed two objects in orbit, two objects orbiting a dead star 900 light-years from Earth, not stars. The masses were too small, far too small, roughly 3 times the mass of Earth and 4 times the mass of Earth, planets. The word planet in 1992 carried a specific set of assumptions. Planets form in the disk of gas and dust that surrounds a young star. They accumulate over millions of years. They are products of a particular set of conditions that exist in the early life of a stellar system before the violence that ends a star's main sequence begins. A supernova doesn't just kill the star, it sends shock waves outward at a significant fraction of the speed of light. It irradiates everything nearby. It disrupts gravitational structures. Any planetary system that existed around the original star before the supernova would, in almost every model astronomers had built, be destroyed or expelled. Either the explosion tears the planets loose from the gravitational system entirely, or the sudden mass loss from the star, supernovae eject a large fraction of the original star's mass, destabilizes the orbits. The assumption going into Wolszczan's observation was not that pulsars had no planets. The assumption was that the question had a clear answer. No, they don't. They can't. The physics doesn't allow it. And yet, there is a moment in research, not often, but sometimes, when the data stops being data and starts being a problem you didn't know you had. When the numbers in front of you are not wrong, but are instead the universe informing you that your assumptions were wrong and that you are now going to have to rebuild. Wolszczan had that moment at Arecibo in January of 1992. He knew what he was seeing. He also knew that claiming to have discovered planets orbiting a pulsar without extraordinary confirmation was career risk of a specific and unpleasant kind. He called Dale Frail. Dale Frail was an astronomer at the Very Large Array, a collection of 27 radio telescopes arranged in a Y shape across the desert of New Mexico, built to see the radio universe in detail. Frail had been conducting independent observations of the same pulsar, not looking for planets, looking for the pulsar's properties, its emission characteristics. Frail pulled his data. He found the same drift, the same periodicity, the same two signals embedded in the timing residuals, two independent observatories, two independent data sets, one consistent conclusion. They published in Nature in January of 1992. The paper was careful, precise, and understated in the way that papers announcing paradigm shifts tend to be when the authors are aware that paradigm shifts require extraordinary evidence. The title was not dramatic. The abstract was not dramatic. The data was. There's something I return to in that moment, not the discovery itself, but the specific texture of Wolszczan's position before the call to Frail. Sitting with data that said one thing, knowing that one thing was not possible, and having to decide whether to trust the math or trust the existing model. That is the actual work of science, not the announcement, the moment before the announcement when you're alone with the numbers and you haven't told anyone yet. The announcement met resistance, as announcements of that kind do. Some astronomers questioned whether the timing residuals could be explained by something other than orbital mechanics, instrumental effects, unmodeled properties of the pulsar itself, interstellar medium effects on the signal propagation. The alternative explanations were investigated. They failed to account for the data. The orbital model held. By 1994, Wolszczan had refined the measurements enough to add a third body to the system, a smaller object, roughly the mass of our moon, orbiting the pulsar at a distance that put it close to the star's surface. 3 worlds around a dead star. The pulsar system is not a comfortable place. The pulsar emits not only radio waves, but X-rays and gamma rays, high-energy radiation produced by the same magnetic field that generates the radio pulses. The radiation environment at the orbital distances of the 2 larger planets, roughly the distance from Mercury to the Sun in one case and somewhat farther in the other, is one of the most hostile environments in the known universe. Nothing lives there. Nothing could. The surface of any planet in that system, if those bodies have surfaces in any meaningful sense, is bathed in radiation that would strip the atmosphere from any world we know. There is no liquid water. There is no chemistry complex enough to constitute biology. The pulsar planets are, by any measure, the most alien worlds we have found. and they were the first. That is the specific irony that sits at the center of this story. The question of whether planets existed beyond our solar system had been open for decades. Astronomers had searched for planetary signals around sun-like stars, stars that might host worlds with temperate conditions, liquid water, the possibility of life as we understand it. The search had yielded nothing confirmed. The technical challenge of detecting a planet around a normal star using the methods available in the early 1990s was severe. And then, planets found around the least life-friendly object in the detectable universe, a dead star, a pulsar, the endpoint of stellar evolution, the wreckage of a catastrophe. The first confirmed planetary system beyond our own was built on ruins. The reason pulsars revealed their planets first is precisely what makes pulsars useful as clocks. The timing precision is so extreme that the gravitational influence of even a relatively small object produces a detectable signal. A planet orbiting a sun-like star causes the star to wobble slightly, a wobble that produces a Doppler shift in the star's light, a shift that astronomers can measure by looking for changes in the wavelengths of specific spectral lines. For a sun-like star, that wobble is small, slow, and buried in noise. For a pulsar, the equivalent signal, the perturbation in timing, is measurable with equipment that existed in 1992. The pulsar found its planets because it was the wrong place to find them, and the wrong place had the right physics. The 1992 discovery did not immediately produce a new consensus about where planets form. The pulsar planets were, and remain, a special case. Most models suggest they formed from the debris of the supernova itself, material that was expelled and then reaccreted around the neutron star, a second-generation planetary system built from the ashes of the first. The original planets, if they existed, were destroyed. These are their successors. But the discovery changed the question being asked. Before January 1992, the question was, do planets exist outside our solar system? After, the question became, how common are they? And the implication, sitting quietly in the data, was significant. If planets could form in the most hostile environment in the universe, around a dead, irradiating, rapidly spinning stellar corpse, then the process of planet formation was not fragile. It was robust. It happened even when it shouldn't. The first exoplanet discovered around a sun-like star was confirmed in 1995 by Michel Mayor and Didier Queloz at the Geneva Observatory. Mayor was at his desk in Switzerland, working through radial velocity measurements of a star called 51 Pegasi, and he saw a Doppler wobble with a period of just over 4 days, meaning a planet completing an orbit in 4 days, closer to its star than Mercury is to the Sun. That discovery won the Nobel Prize in Physics in 2019. It is the canonical exoplanet discovery in most popular accounts of the field. Wolszczan and Frail did not win the Nobel Prize. Their discovery is often footnoted, treated as a curiosity, a prelude to the main story. The argument is that the pulsar planets are so exotic, so far from the question of life in habitable worlds, that they represent a branch of the story rather than the trunk. There's something about that framing I find insufficient. The discovery of the first extrasolar planets was the discovery of the first extrasolar planets. The physics doesn't care about our preference for where they turned up. The universe demonstrated that planetary systems exist beyond our own in the most inhospitable address it had available. And the lesson in that is not a footnote. It's the finding. Wolszczan was not looking for planets. This point deserves more weight than it usually receives. He was studying the pulsar's properties, its dispersion measure, its polarization, the details of its emission mechanism. The timing residuals he was analyzing were a standard part of pulsar characterization. The anomaly in those residuals was something he was trying to explain away, not something he was hoping to find. The history of astronomy is full of this pattern. Caroline Herschel, working at her brother William's observatory in the late 18th century, discovered 8 comets while cataloging nebulae. Jocelyn Bell Burnell, analyzing radio telescope data in Cambridge in 1967, found a signal that pulsed with unnatural regularity while searching for something else entirely. And that signal turned out to be the first known pulsar, which is to say, the first known neutron star, which is to say, an entirely new class of object. Arno Penzias and Robert Wilson, trying to eliminate noise from a radio antenna at Bell Laboratories in New Jersey in 1965, found a persistent hiss that turned out to be the cosmic microwave background, the thermal afterglow of the Big Bang itself, the oldest light in the universe, detectable as static. The discoveries that change the frame are rarely the ones that were planned. They are the residuals, the anomalies, the things that don't fit and won't go away. Wolszczan's timing residuals were the universe declining to behave according to the model in a sufficiently structured way that the structure itself became the discovery. The drift in the pulsar's timing was not a flaw in the data. It was the data telling him something he wasn't asking. That's the part that matters to me most, if I'm being precise about it. Not the discovery of the planets, though that matters obviously, as a fact about the universe, but the epistemological structure of the moment. The way science actually moves is through exactly this kind of encounter, a measurement that doesn't fit, an anomaly that resists explanation, a residual that refuses to disappear. The neat narrative of hypothesis, prediction, confirmation is real, but it is not the whole picture. A significant fraction of what we know came in sideways, through the wrong door. How do the planets exist at all? This question has a partial answer, and the partial answer is instructive about what we don't know. The leading model is that the pulsar planets formed from fallback material, debris from the supernova explosion that did not escape the gravitational pull of the newly formed neutron star. Some fraction of the ejected mass fell back. Over time, this material may have formed a disk around the pulsar, and within that disk, the same process of accretion that builds planets around young stars operated again. Dust grains collide and stick. Clumps form. Gravity pulls clumps together. Given enough time and enough material, planets emerge. The problem with this model is that it is not confirmed. The timescales involved are long, billions of years, and the initial conditions of a post-supernova disk are poorly constrained by observation. The disk, if it existed, is no longer detectable. What remains is the end product: 3 bodies orbiting a neutron star, the fact of their existence as the primary evidence for the process that produced them. There is a second possibility, less favored, but not ruled out. The pulsar may have had a binary companion, another star, orbiting it, and that companion may have survived the supernova in a disrupted form. Tidal forces and mass transfer could have produced a disk from the companion's material rather than from fallback debris. Some calculations suggest this scenario is more plausible for certain orbital configurations. The honest answer is, we know they're there. We know they're orbiting. The precise story of how they arrived is unresolved. The formation of second-generation planetary systems around neutron stars is a field that has exactly one well-confirmed data point, the system Wolszczan discovered, and one data point is not a statistics problem. It's a beginning. In the years following 1992, the confirmed exoplanet count grew slowly, then quickly. Then in a way that made the question of planetary rarity feel retroactively absurd. The Kepler Space Telescope, launched in 2009, monitored more than 150,000 stars simultaneously for the tiny dimming caused by a planet crossing the face of its star. By the time its primary mission ended in 2018, it had confirmed over 2,700 planets, with thousands more candidates awaiting confirmation. Current estimates, based on statistical analysis of Kepler's data and subsequent surveys, suggest that most stars in the Milky Way host at least one planet. The galaxy contains roughly 200 to 400 billion stars. The numbers are not a comfort or a threat, they are simply what the data says. The pulsar planets, in this context, are early coordinates on a map that turned out to be enormous. They were the first confirmed points on a map we didn't know we were drawing. Their discovery didn't cause the subsequent revolution in exoplanet science, the discovery of 51 Pegasi b, and then the Kepler mission, and then the systematic application of radial velocity and transit methods, but it established that the question had an answer, and the answer was yes. Before 1992, the existence of planets outside the solar system was a reasonable hypothesis with no confirmation. After, it was a confirmed fact. The confirmation happened to come from the most extreme environment in the known universe, but the fact itself was clear. Wolszczan is still working. In the decades after the 1992 discovery, he continued refining the timing measurements of the pulsar system, tracking the stability of the orbits, looking for additional bodies, watching the system evolve. The pulsar's timing is precise enough that small perturbations, gravitational interactions between the planets themselves, relativistic effects from the neutron star's gravity, are detectable in long baseline observations. The system is a laboratory, not for biology, not for the possibility of life, but for orbital mechanics in extreme gravity, for the behavior of matter at neutron star densities, for the physics of planet formation under conditions no terrestrial experiment can replicate. The pulsar planets are useless for any question about habitability and invaluable for questions about planetary systems as physical structures. There is something clarifying about that. The universe does not organize itself according to what we find useful. It produces what the physics produces in the environments where the physics produces it, without reference to our preferences for where interesting things should happen. A gravitationally collapsing stellar core produces a neutron star. Debris around a neutron star, given time and the basic mechanics of accretion, produces planets. The fact that those planets are uninhabitable does not make them less real or less informative. It makes them exactly what they are: evidence. The evidence says that planet formation is not a delicate process requiring specific gentle conditions. It is a robust process that happens wherever the raw materials and the gravitational environment allow. It happens around young stars and around dead stars. It happens in the quiet outer arms of the galaxy, and presumably in the crowded galactic center. It happened at least once in the aftermath of a catastrophic stellar death, around an object spinning 9.5 times per second, bathed in radiation at the other end of a supernova. If the process is that robust, the implications for distribution are significant. Not for life. Radiation environments like the pulsar systems are not conducive to the chemistry of life as we understand it. But for the basic question of how common worlds are, the answer is very. The answer is, wherever physics allows, worlds appear. "900 light years. That is the distance to the pulsar system. Light traveling at just under 300,000 kilometers per second takes 900 years to cover that distance. The radio pulses Wolszczan was analyzing in 1992 had left the pulsar around the year 1090, roughly the time of the Norman conquest of England, roughly the time of the Song dynasty in China. They had traveled through interstellar space for 9 centuries before arriving at the dish at Arecibo and being recorded as a structured anomaly in a timing residual. The planets were there during all of it, orbiting, completing their circuits around the dead star, silent, as everything is silent in the vacuum between stars. The timing of their orbits encoded in the signal that had been traveling toward us since before universities existed in Europe. The discovery was not that something new happened in the universe. The discovery was that something old was already there, already real, already complete, and we had the instruments to read it for the first time. That is what I mean when I say the question of planetary rarity feels retroactively absurd. The planets didn't appear when we found them. They had been there for billions of years, long before any nervous system existed on Earth to ask whether they were there. Our discovery changed nothing about the universe. It changed only what we knew about it. The universe didn't wait for a comfortable address to start building worlds, and neither should we.